Okay, these are practice questions on page 53 of the notebook packet, 1 and 2, about enthalpies of aqueous solution. So the enthalpy of aqueous solution is actually pretty straightforward. It's the enthalpy, the lattice enthalpy of an ionic compound plus the hydration enthalpies of both of the ions. And then it takes into account any mole coefficients that you need to take care of to balance everything out. So the lattice enthalpy of calcium fluoride, we should know, is the enthalpy change when calcium fluoride solid, 1 mole of it becomes calcium ions and fluoride ions that are gaseous. Right, so you need to make sure you move little subscripts into coefficients when you separate these ions apart. So that's a lattice enthalpy. That's in table 18 or section 18 of the data booklet. I'm not going to turn there now, but it's for this one is 2651 kilojoules per mole. That's a positive value. Lattice enthalpies are always positive because you're separating apart these ions which have strong ionic bonds between them. Then I need to look at the hydration enthalpies for both ions. So I'm taking calcium ions, which are gaseous, and turning them into calcium ions that are aqueous. I don't show the water involved, I just show the change. That's always an exothermic change since you're forming attractions, you're forming like ion dipole attractions between water molecules and ions. It's always exothermic. These enthalpies of hydration are in table 20. So if I go up here, I might as well find the fluoride one at the same time. So table 20, enthalpies of hydration, and you'll see they list positive ions on the left, negative ions on the right. So calcium minus 1616 and fluoride is minus 504. So come back down here. This one was minus 1616 minus 504. The one thing that I need to do with the fluoride, and again it's just the fluoride ions going from gaseous to aqueous, is that because there's 2 fluoride ions in the calcium fluoride compound, I'm going to need to do the second hydration times 2. And that way, if you think of this in terms of simultaneous equations, the gaseous fluoride ions will completely cancel out, and it will be overall balanced with what I'm trying to solve for, which is the enthalpy of aqueous solution. If you go through this and you cancel things out, you'll see the gaseous ions are gone, and you're left with the solid ionic compound becoming aqueous ions. And that's what happens when we dissolve an ionic compound in water. The solid becomes aqueous. So we're using these other enthalpy changes to solve for what this enthalpy change might be. If I quickly do this without mistakes, let's see, so I get so I'm adding those to, let's see, minus. I can do it. Okay. Overall, I get an answer that is positive 27 kilojoules per mole. So according to our calculations, dissolving calcium fluoride in water should be an endothermic change. The lattice enthalpy is a little bit larger. This one's a little bit more positive than these ones are negative. So that's overall what we get. Usually the enthalpies of aqueous solution are much smaller in magnitude compared to the lattice enthalpy and the hydrations. Okay, question number 2. We've got potassium nitrate. Again, I've been given the lattice enthalpy here, so that's going from KNO3 solid to K plus and NO3 minus. So I should be comfortable writing out chemical equations to represent these changes. That's positive 640. Then I have to look up the hydrations of potassium and nitrate. Those are in table 20. So potassium is, this would be going from K plus to K plus aqueous. That's minus 340. NO3 minus gas to NO3 aqueous. And that value is minus 316. No mole ratios to worry about here. Everything is 1s, so that's about as simple as it can get. Those gaseous ions all cancel out, and I get my overall enthalpy of aqueous solution dissolving potassium nitrate in water. Okay, and let's see really quickly, I can see the negative ones add up to negative 656. And so overall, this one is going to equal negative 16 kilojoules per mole. So maybe one like this could be on paper 1 if the numbers aren't too complicated. Obviously, there could be a slight twist here where maybe in an example where a lattice enthalpy isn't listed in the data booklet, like this one, so potassium nitrate, instead of solving for this enthalpy of aqueous solution down here, they could give you the enthalpy of aqueous solution, and they could have you solve for the lattice enthalpy here. Okay, so you should be aware that for this energy cycle, it's the enthalpy of aqueous solution, which is just dissolving 1 mole of an ionic compound in water, is equal to the enthalpy, the lattice enthalpy, plus the enthalpy of hydration for the cation, and the enthalpy of hydration for the anion. And then you take into account any mole ratios needed for these hydrations. So those are just, it's a pretty straightforward enthalpy cycle, or energy cycle. If you need to solve for the lattice enthalpy, you should be able to do that with some simple algebra. You would take the aqueous solution and subtract out the enthalpies of hydration. In the video, I do mention about the enthalpy of hydration. They could ask you to write out its equation or define it, right? It's pretty straightforward. It's taking 1 mole of gaseous ions, converting it to a mole of aqueous ions. It's always exothermic because these attractions are being formed, and the factors that affect it, if you look at these tables, are the exact same factors that affect lattice enthalpies. So it's an increase in charge and a decrease in radius, ionic radius. These both lead to an increase in the enthalpy of hydration, because the same factors that affect attractions between ions affect attractions with water molecules. And so if they ever ask you why, it's again coming back to the idea of increasing charge and smaller radius creating greater charge density and greater attractions.